All right, folks, this is the conceptual part of the vertical springs lecture, and I'll do the example problem in a second video. And just quickly, clearly the title is vertical springs, and there's no new formulas in this lecture, but there's a lot of critical points. So please take careful notes. All right, you don't need to write this down, but just a quick visual. Up to now, if you go back and look at all the problems I've assigned so far on spring stored energy, it was objects moving back and forth at the same height. So like the plane coming in for landing or the person on rollerblades with the two springs. So as the spring stored energy changes, the gravitational energy doesn't. So we don't have to deal with both at the same time. And the classic example problem is a bungee jumper. So if you set the lake as sea level, then as the bungee jumper, or pretend like they're still connected to the bungee jumper, as let's say this is unstretched, we're always going to mark that with a dashed line. That's where the bungee wants to be. And as the person stretches that bungee, you can see that they change both the delta x in the 1/2 kx squared, but we're calling it y. You don't have to, but y is just indicating the bungee's moving up and down instead of left and right. So that is clearly changing, right? More and more energy in the bungee, less and less energy in the bungee. But they're also changing their height. So again, I'm just calling the height y instead of h. They're also changing where they are relative to whatever you define as sea level. Okay, so what I want you to see, the reason I call these both the same variable is we're going to have one term that varies with y, and we're going to have another term that varies with y squared. So at almost all locations, the exception is going to be when you're at sea level, your total mechanical energy equation will be a quadratic. So when you are solving for the location that something happened, you're going to get two answers. And if you don't have a quadratic equation, then you might have oversimplified the problem. Okay, so that is warning hint number one. All right, and now we're going to look at different specific points. You should take really careful notes because each of these points is going to be what we call a critical point, where something interesting is happening or there's something particular you need to know, like we did before, like turnaround point means v equals 0. Okay, so it's really important that you lock that information in. Okay, so vertical springs don't have to be a bungee jumper, but we are familiar with bungee jumping, so we're going to call the point that they start on the bridge point A. At some point, I'm calling that location B, the bungee engages. So that is unstretched. So this distance here would be the length of the bungee jumper. I'm sorry, the length of the bungee cord. All right. I highly recommend that you decide that you label the unstretched location of the spring to your gravitational potential energy relative, like sea level. That's where height is 0, which is kind of counterintuitive because your gut would probably want to mark the bridge as h equals 0 because you may not know how far down they go. Your brain may really want to set this as h equals 0, but often we don't even know that distance. Okay, so it's really counterintuitive, but if you look over here, the reason we do that is then your UG is relative to this height. So MGY, Y is a distance above or below that, right? So Y could be negative, could be positive. And your spring stored energy is going to be 1/2 k y squared. These are the same variable. Okay. Otherwise, you have to make some correction of like, it's really the height minus the length of the bungee or something. So you may set sea level to wherever you want. It's not going to be mathematically wrong, but your algebra, you're going to have more terms. Okay, so I highly recommend you set unstretched to sea level. All right. Oh, I didn't go through the rest of the point. So then first there's unstretched. C we're going to see is equilibrium, and D is your bottom turnaround point. So if you want to pause the video and like mark all those points. Okay, so we're going to look at point E, which is equilibrium. Equilibrium is a specific point. We're not going from one point to another. So that's a hint that this is about forces. So we're going to draw a force diagram for the bungee jumper. And everything has weight. And the bungee is pulling back up with a force equal to K delta X. I'm going to quickly say, technically, if you're paying attention, the formula is F equals negative K delta X, but delta X is below sea level. So that delta X is negative, and the minus sign in front is going to be a double negative. So in general, like that to me, having all the minus signs floating around is just, you'd be more prone to error. So I always just say I am labeling the magnitude of the force, and I'm ignoring all the minus signs because it needs to be positive. And I know that the force of a spring always points to unstretched. So I'm just going to use my force diagram to indicate the direction. Okay, and since this is equilibrium, if the question is to actually calculate this distance, let's call it delta x e equilibrium, you would set these two equal and solve for delta x. All right, so that's what's true at equilibrium. The force of the spring, the pull from the bungee, is equal to the pull from the earth. Okay, and that point D is a lower turnaround, right? And you hope that's above the water. So what energy term is zero at point D? Since it's a turnaround, your velocity is instantaneously zero, which means your kinetic energy is going to be zero, which is going to make the problem easy to solve, right? Because you're getting rid of a term. All right, so now we're going to look at the bungee jumper from A to B. If you go back to your picture, where the bungee has not yet kicked in. So actually, let's do it here so we have more room. So in your notes, I would suggest, you draw this whole picture, and then if you didn't leave yourself enough room, just draw a little arrow. And in that whole region, however big it is, the earth is pulling down on the bungee jumper, but the bungee's slack. So there is no tension in the bungee. Or K delta, delta X is zero. It's not stretched or compressed. Okay, so if you apply sum of the forces equals ma, they are in free fall. And maybe that term means something more to you now because they're free from all the other forces except for gravity. So the earth is pulling down. The arrow is indicating negative sign on the diagram. We need to put it in ourselves in the calculations. And then, shocker, we get that the person is accelerating downward at 9.8 meters per second squared. Okay, so please write this down. Our velocity is down. It starts at zero, but every other instant velocity is down, and the acceleration is down. So since V and A are pointing in the same direction, the bungee jumper is speeding up at a constant rate. Okay. Okay, there we go. Bungee jumper is speeding up. Okay, now we're going to go from B to C. So this is the really important point. From B to C, C is equilibrium. So the forces aren't equal yet, and the spring force is increasing. So force diagram, the weight is the same. And if you want to make up a number, let's just say it's 100 newtons even. And K delta X is not constant. It is slowly or quickly, depending on your reference point, getting bigger, bigger, and bigger, but is always less than 100 newtons, right? Because they're equal to each other at equilibrium. I just made up the 100 newtons. Okay, so it's approaching equilibrium. So mg is going to be greater than K delta X. So the person's speed is down, and until they reach equilibrium, the net force is also down. Okay, so V, yeah. Sorry, I want to see what was on. V is down, or sorry, V and A are going in the same direction. But the forces are getting closer and closer to balance. So velocity vector is getting a little bit longer each time because V and A are in the same direction. Sorry, I'm a little bit jumping around here. So V and A are in the same direction, so therefore speeding up. So the velocity vector is getting a little bit longer, but since the forces are getting closer to balance, that acceleration vector is actually shrinking with time. Oh, dang it. I was trying to impress you with have it slowly erase and it's not working. The acceleration vector is getting smaller and smaller and smaller. So what I'm trying to say, it is speeding up at a decreasing rate. Okay. Which we'll talk more about at the end of the year when we do calculus, but there is a trick question that if you are, well, if you're driving in your car, if it's a horizontal problem, as soon as the seatbelt engages, because you stop quickly, you will slow down immediately, right? Because the force and velocity are opposite the motion. But if you're bungee jumping, you will feel the bungee engage, right? So when you're driving your car, you're like, oh, my seatbelt is pulling on me. I must be slowing down. You will feel the bungee engage, but as long as mg is greater than K delta X, you're still speeding up. Okay. That's what I want everybody to know. That's a classic trick question on the AP. But I think it's important for a couple of reasons. Just look at to understand force diagrams, to understand that, anyway, if there's multiple forces, you can't assume which force is winning. All right. So I don't get too distracted on that. Okay. So, all right. So now we've sped up for a little bit of time, and then for an infinitesimal amount of time, we pass through equilibrium. So often equilibrium means something is just sitting at rest, right? Something's sitting at rest, air conditioner sitting at rest on top of this building, and it's at equilibrium for a long time. But it is absolutely possible to pass through equilibrium because you got inertia and you've got speed, right? So no guarantee that when you're at equilibrium, you're at rest. Equilibrium doesn't mean rest, which is V equals 0. Equilibrium means the forces are balanced, which means A equals 0. And it is really, really common to confuse those two things because often both are true. You're sitting there chilling, you're not moving, and your acceleration is 0. Not the same thing. Okay, so now we're going to go from C to D, which is after we've passed through equilibrium. So C to D, I still have a weight. I just made up a number to make this more concrete. So the Earth is still pulling on me with 100 newtons. We've passed equilibrium, so the delta X has gotten even bigger. So K delta X is bigger than 100 newtons. Right? So the person is still headed down. We were making the velocity vector orange. Still headed down, but now the up force is bigger than the down force. So now my acceleration vector is pointing up. So A and V are now in opposite direction, which means that the bungee jumper is slowing down. And if you want to be technical, at I think, increasing rate, because K delta X is going to be winning by more and more and more, so your acceleration vector is getting bigger. All right. K delta X is bigger than mg. The net force is opposite the motion, and therefore there's more negative work done than positive work done. So in summary, if you haven't written this down yet, when you bungee jump, you feel the bungee engage before you begin to slow down. As long as mg is bigger than K delta X, you are speeding up. All right, so if we go look at this, you were accelerating at 9.8, then you were speeding up, then you were slowing down. So this is where you hit peak speed. Okay, so the hopefully that makes sense. I realize I'm at 16 minutes. So okay, this is really, 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 really important. And this is the last slide. Your maximum speed, write this down, will always occur at equilibrium. Okay. We figure this out from the force diagrams, right? From when you were speeding up, when you were slowing down. You can also prove it using calculus. I'm going to talk about that super briefly. We want to find the maximum speed. So the velocity is a function. It's not a linear function, as we saw that we're going to see it's a sinusoidal function. But it is some function of time, right? How do you find the maximum value of a function? You take the derivative of it and set it equal to 0, which could be a min. In this case, it's a maximum. Because what is the rate of change of acceleration of velocity? That is acceleration. So this is not a coincidence, because definition of equilibrium is that the acceleration is 0, which means that the time derivative of velocity is 0, which means that the velocity is either a max or a min. Okay, that is really important. Some of the AP problems and some of my problems on the test, you need to know this. This is a fact. This is a concept. The problem may not say, find equilibrium, explain why that's the maximum speed. It may just say, find the maximum speed. And that is a two-part problem. It means A, find equilibrium, which is about forces, because that's the definition. It's when the net force is 0. And then step 2, conserve energy from A to equilibrium. Doesn't have to be point A, but some point A, B, C, D, with some other point to solve for V. Okay, so just like finding max height was a two-part problem, that was setting V equals 0 and then finding the position, right? We're just going back one derivative. Finding the maximum speed is setting A equals 0 and then solving using energy to solve for V. Okay, super, super important, really critical idea. Hopefully this all makes sense, and thanks for listening.